Okay, 3216 says we have a circuit, an LR circuit. It has, let's see, it has a battery, an EMF of 12 volts, and it has a switch so that we can define when time equals 0, and it has an inductor with inductance that's going to vary. We'll think of a few different kinds of inductance. And it has a resistor R equals 24 ohms. And it says it wants us to think about, actually wants us to plot what the current does for 3 different kinds of inductances. When it's roughly equal to 0, when it's roughly equal to sort of an intermediate value, and when it is roughly big. Or we could say it's roughly infinity, if something can be roughly infinity. So to do this, first thing we ought to write down is the current. We already solved for the current in one of these circuits. And we know that this is a case where it's going to grow from 0. If the current is 0 when you throw the switch, and it sort of grew up to some saturating value. And we solved the equation, and it looks something like the EMF over R times 1 minus e to the minus t over tau, where we said tau was the time constant that describes the behavior of the circuit. So tau was L over R, where the inductance and the resistance come in. So we can make these plots 2 ways. We can do it intuitively, and we can do it mathematically. So let's do it both ways. Let's first just plot the first case. Here we have time. Here we have current in amps. Let's do the case where L, the inductance, is pretty much equal to 0. That means it's sort of like there's no inductor here. It has a very little effect. Well, what would happen if there's essentially no inductor, there's just a wire there? You throw the switch, you're going to get a current that's going to go up very quickly and give you a current value of 12 volts over 24 ohms. So what it would basically do is here would be 0.5 amps. That's equal to E over R. 0.5 amps. So at t equals 0, here, if this was before you threw the switch, it would be 0. And then suddenly the current would very quickly jump up to 0.5 amps, and it would just sit there and go at 0.5 amps. What if L were some value that is intermediate? And what that basically means is it has a reasonable value. In henries, it might be a Henry or 2 Henries, something like that. And what it also means is when you take this reasonable value over that reasonable value, you get a reasonable value. You get some time constant that's on the order of seconds, say. Well then, that means that this term is important. And that means it'll take the shape of the curve that we considered before, where if this is 0.5 amps again, this is again EMF over R, that represents sort of the limiting value that you can get. And we talked about this curve before, it just comes up and it exponentially approaches that limiting value. If this was t equals 0. It was flat before that. So those aren't lined up, right? And the exact rate at which it does this, how fast it takes it to get there, depends on the exact ratio of L over R. And since we weren't given L, we can't do it with numbers. This is L equals the intermediate value. All right, and now at the bottom of the board, we're going to squeeze in the case where L is essentially very large. L is infinity, and I'll put t equals 0 here. I should have it before. This is the current in amps. Here again is 0.5 amps. So this is the limiting value that you will never reach. But now that L is so big, the time constant is big. If the time constant is big, let's see, time constant is big, that means it'll basically never get there. It'll take a very long time. This thing will come up very slowly. Because the thing has so much inductance, it creates a very large counter EMF. It takes a very long time